My dear students, for Btech, in the environmental part to almost the design of the physical treatment like sedimentation, maybe grit chamber, primary sedimentation, secondary sedimentation, then in the water treatment plant, like the clay flocculators, in the wastewater treatment plant, like the secondary sedimentation after the biological process is over. The secondary part, that is the biological process, design of drinking filter in activated stress process over. So almost it is done. Now, some of the miscellaneous treatment that is not in the water treatment plant nor in the wastewater treatment plant. Some miscellaneous treatment. Okay. So now I'll be going with septic tank. So before designing, let me explain what is a septic tank. Okay. Septic tank is the anaerobic biological process that's going on always in our toilet to digest the human sludge. Okay, before designing it, let me explain you. This is a septic tank, and here it is going to be anaerobic. That is completely devoid of no oxygen. Okay, especially for human waste. Okay, so what's going inside the design of a septic tank? It's not going to ask what is a septic tank. You can find in a notebook by yourself. You can Google it out. So from design point of view, the septic tank before designing, let me give you the basic fundamentals. The septic tank, rather I'll say, it comprises of three zones. Okay, this is zone number 1, this is zone number 2, and this is zone number 3. The waste is going to come from here, it's going to flow, then after treatment it's going to go out from here. Okay, how it looks inside different partition, that's a different issue. See, the moment the human sludge, human waste is coming over here, or we call it sometimes soils, also night soils. Here, all these human soils, these are nothing. These are the BOD or the COD. This is going to be the reaction zone. Here, all the biological process by the anaerobic bacteria will be happening. This BOD, COD are the food of the microbes. These are the microbes. What microbes? Anaerobic. Okay. They are going to eat the things. So this required some particular detention time or HRT. If you want to eat a food from your plate, I have to give you some time. I just cannot give the food to you and I cannot take it away. 5 minutes, 10 minutes, 20 minutes, I have to give you some time. If you want to eat more, if your capacity is very high, I have to give you more time, right? So some HRT has to be hydraulic retention time has to be maintained over here. Hydraulic retention time, or sometimes over here we call it is not actually hydraulic, but rather we call it detention time. Detention of the wastewater over here. Okay. In the future process, this BOD and COD will be eaten by the microbes, and all the microbes will start settling at the bottom. And this microbes, we call it the sludge. Day by day, the microbes will start eating it and the sludge will be here and the sludge will start increasing, correct? And this part, we call it the freeboard. We keep it around 300 mm. Or you say 0.3 meter to 0.4 meter for air, okay, for easy flow. Now, this sludge also, do we need to retain the sludge over here? No, we don't have to retain the sludge because here automatically it's going on. The biomass, the sludge settled at the bottom is of no use. Then, should we remove it? Yes. But the thing is, it is not very feasible for us to remove the human sludge, the digested sludge. This is called the digested sludge. Okay, not exactly digested, but the digested part. It is not feasible for us to remove everything because it's very smelly. It's not environmental friendly. So what we do is we keep it here for a long time, and every family, we common peoples, we don't have the facility to remove the sludge. What we do, we call the municipality people to take the pipe inside and to suck it out everything, right? So this sludge, what we do is we keep it for maybe if you want to clean for after 1 year, okay, 2 years, okay, 3 years, okay, but we don't clean it every month. It's going to create a lot of ruckus in the society with all the smells, right? And this sludge contains the cells plus water, and the cells solid. This will be around 2 to 4%. Okay, clear. So when we design a septic tank, the first thing what we have to remember is this zone has to be designed for HRT of how much. So from the experience, it is known that the HRT or the detention period can be kept for around 24 hours. So the human sludge, it takes around 24 hours for the microbes to eat it up and to digest it. So detention time is around 24 hours. And remember, I always say the operational parameter designed for any of the reactor, primary, clarifier, secondary, whatever, it is always number one is the cycling velocity, number two is the hydraulic retention time. So over here, we are going to use the detention time. Okay, so based on the detention time of 24 hours, we are going to find the volume. So how much volume is it? We are going to calculate. Second thing, what should be the volume of this? The volume of this means you can decide whether you want to keep it for 1 year or 2 years or 3 years. That is called desludging period. Desludging period. Okay, means we are going to remove the sludge. But how do you know that how much sludge is coming? So it is maintained that around the sludge is around 30 to 40 liters per capita per year. You please note it down. These are certain assumptions, not assumptions, but certain points which you have to note it down. Every human, if he use a particular toilet, from the toilet, the digested sludge, the sludge that is settled at the bottom, will be around 30 to 40 liters in a year. Is it okay? So when we go to the toilet, we flush around 5 liters of water or 3 liters of water from our cistern. So that is going to be over here, and the human waste, after degraded by the microbes cells around 2 to 4% is going to mix with the water. This sludge part will be around 30 to 40 liters per human being per year. You may argue with me, sir, we don't go to toilet in a particular. Sometimes I may go to my hostel, sometimes to the hotels. That's correct. But during the design, we cannot create all these small issues. We are taking everything average. Okay, is it fine? So based on this, we are going to calculate. And another one is this cleaning. Cleaning, if you say, sir, I want to do it after 5 years. No, it should not be. If you don't desludge, the volume of this sludge will increase, and it is going to minimize the volume of the reaction zone 1. This zone 1 will be minimized. So we don't want that. What we do is, next is desludging. Minimum we do is when it is full capacity divided by 3. That means full capacity means 1 plus 2. When this around 1/3 is occupied, then we do desludging. If it's more than 1/3, then it becomes a problem for this reaction. Then what will happen is the volume of this will be very small, and before the reaction itself, the sludge may escape out. Okay, so this lesson is also done always around when 1/3 is full. So these are the points you have to remember for designing it. Okay, clear? And freeboard is just an extra. And next one is depth. We kept it around 2 to 2.5 meters. We don't want to keep it for very, very long depth because cleaning is a problem. And it should not be, if you make it for 4 meter depth, no problem, it will be very effective. But while cleaning, 4 meter means around 13 feet. If people falls down in the sock pit, it will be a problem. Okay, so from a convenience, we make it around 2 to 2.5, and the length is to breadth. We make it around 1 length to breadth. It may be any length. So if you consider this as a length, then as a breadth, we make length to breadth is equal to around 4:1. We want to make this one longer so that the water will keep moving and then it will go out. Okay, this is for convenient. So you can write some of the points. Number 1, number 2, number 3. Detention is around 24 hours. Number 4, desludging when it is 1/3 of capacity. Okay, and then some points you have to remember. Number 5 is say, what is that? The sludge is around 30 to 40 liters per capita per year, not per day, in a year. Okay, these are the points you have to remember for designing a sludge. Septic tank. Okay, now let me start designing the septic tank. Pause the video if you want to have a look. Let me rub it out. Okay, I'll design in 2-3 different ways so that you can understand from all the sides. Online teaching is not very healthy communication, but I feel if the online teaching is going to continue for another 2 years, once I click the video, I can sleep for another 2 years since I have uploaded almost all the videos. Only interaction I require. Okay, that's fine now. Now, say for example, simple. You are a civil engineer, you are an environmental engineer. To design a septic tank, you don't have to collect the data. Simply one of a frame or one of the, say, someone who's going to build a house or someone who's going to build a community toilet, they'll come to you and say, sir, kindly design a septic tank for us. What else they will bring the data? Nothing else. They'll say you only one thing. They will say, sir, please design a septic tank for 100 people. The reason is, say for example, if you try to have a society, in a society how many buildings may be there? There may be around say 20 flats. It's flat at average, it will be 5 members, right? So 25 is 100. So if you are a builder, you are going to construct a septic tank, you are going to make for 100 people, right? So, sir, please design a septic tank for 100 people. That's all. He's not going to say anything. So now, the first thing is you have to decide. I told you there is 3 zone. The first zone is the mixing zone. Second is a sludge zone. Third is freeboard. Freeboard, you just can increase the depth. That's all. So, first one is the mixing zone. the volume, strain. What is volume? Volume is called the Q into T, right? What is T? T, detention, you assume as, I told you, 24 hours, correct? 24 hours. Huh. And then what about the Q? What is the discharge? Discharge, they will give or they will not give. Discharge is something that is very important. Without discharge, we cannot do. That is, how much discharge is going to be there per day or per day per human. Okay. So remember what we say is, if Q is water demand, then the Q waste is going to be around 80%, right? Maybe 70 to 85%. And you know, water demand is always 135 liters per capita per day. This is standard. If you are making a society, this will be the standard. So 80% of this, fine. So if you say 80% of 135, how much? 85 to 40, 83 to 24, it was 8, 9, 10, 108, right? Liters per capita per day. So my dear friend, what I'm trying to say is, always remember that the Q is around always 100, or I'll say 90 to around 120 liters per capita per day. Okay, this is a side business. So can I say Q is equal to, you assume for easy calculation, 100 liters per capita per day. It's in a day. Okay, so very easy. Volume is equal to, I'll say volume 1, or I'll say volume mixing. Volume mixing is equal to 100 liters per capita per day into time. Time is 24 hours. So I will say this is 1 day, correct? So this itself is per percent. So into 100 capita, that is 100%. So this becomes 10,000 liters. Number 1. Okay. So the one volume is fixed. Number 2 is sludge zone. In the sludge zone, already I have told you, this 90 to 120 liters per capita per day, this wastewater is going to become as 30 to 40 liters per capita per year as a sludge. So in a sludge zone, let's say 30 liters per capita per year. Okay, now see, it's equal to 30 liters into 100% per year. This is equal to 3000 liters per year. Now the question comes, every year you require 3000 liters. So now the next question comes, this year sludge, when are you going to clean it? Either the cleaning should be when the capacity is 1/3 full, or if you say I want to clean very year early, so let's assume, or you say to the builder, you have to de-sludge every 1 year. Cleaning or de-sludging is equal to 1 year. You have to clean every 1 year. It's optional. If if you clean every year, then the volume will be small. Therefore, volume is equal to volume mixing plus volume sludge is equal to 10,000 plus. If 1 year man, then this will be 3,000. Correct? So this is 13,000 liters is required. This is the effective volume. That's all. Design is over. Have a look. Very simple. Okay. Now I am going to go. The design means volume is known. You have to go for the length and the breadth. And you said that you clean it every 1 year. If 2 years, you can put 2 years. That this will be 6,000. So this will be 10 plus 6 will be 16,000 liters. Okay. So now you see over here. Now we are coming to dimension. For a dimension, you make depth is called the 2 meter. Therefore, area is called the volume by depth is equal to 13,000 liters by 2 meter. So 13,000 means this is 6.5 meter cube. Okay, 13,000 liters means 13 meter cube by 2 meter, right? So 6.5 meters squared is the area. Length is to breadth is called to 4:1. Therefore, length by breadth is called to 4. Length is called to 4 breadth. Therefore, length into breadth is called to 6.5. Length is 4b. 4b square is called to 6.5. Therefore, breadth is equal to 6.5 by 4 root over. .5 divided by 4 is equal to 1.27. It's equal to 1.27 length. Okay. Breadth is equal to. Therefore, length is equal to 4b. What is this? 1.27 meter. Therefore, length is equal to 4 into 1.27. 4 7 is 28. 4 is 8, 19, 0, 1 kg. 4 is 4, 5. Okay. Is it clear? So, length you got it, and breadth you got it. Therefore, length is equal to effective length plus 0.3 meter for the freeboard. Therefore, length is equal to how much? 5.08. 5.08 plus 0.3. This can be 5.38, and it is approximately 5. Oh, I'm very sorry. Length is correct. Therefore, L is equal to 5.08 meter. Breadth is equal to 1.27 meter. Depth is equal to 2 plus 0.3 for the freeboard, that is 2.3 meter. Finished. Your septic tank is over. Okay. Okay. So design of the septic tank is over, but the septic tank has to be designed by the concretes. This is one material instrument. Let me check whether the video is still on. Thankfully, it's still there. Okay. Now let me go with the another next design. Sometimes in the villages we design something called sock pit. Sock pit means we just dug it out. We put all the human waste over here. What happened is this soils, this liquid waste, they percolate. Okay, they percolate into the soil, and we also put some sandy materials so that percolation will be fast. So if you have to design a sock pit in a village, it is very important to know what is the percolation or percolate means percolation rate. You have to do an experiment. Simply, what you have to do the experiment is put the liquid and see how much liquid is gone, and the unit will be how much liter of the water is percolate per unit square area per unit time or day or hour. In a particular time, in a particular square area, how much liter of the water has been percolated. So the more is the percolation, you can unclean it for a long time. Okay, so you can design one socket for the same thing. Okay, so this one, it is around 1,200 to 2,000 liters per meter square per day. Correct? Oh, my earphone is coming out. Oh, where is my earphone? So let me check the microphone. Still, it's working. It's clear. Huh. So it is around 1,250 liter per meter. Oh, it's not meter cube, but it's meter square. Okay. Percolation rate. So just now, if you have to design for 100 peoples, this is 100 peoples. Okay. So for 100 peoples, what we do is we say that one person, it gives out around 100 liters per capita per day wastewater. Okay, so now you have this, and the percolation rate, you have this. This is to be assumed, and you may say, sir, why should we assume the percolation rate of a particular place? We don't know. How do we assume? The thing is, you are not going to make a sock pit, number one, nearby a river, it's going to dilute. Number one, you're not going to make in the Rocky Mountains. You're going to make a percolation sock pit definitely where the soil permeability is very high. So we always prefer in this range. Otherwise, you have to go and do a test over there. If from exam point of view, if no value is given, you can assume this way, or they will give you. Therefore, see, from here, there is no definite formula. You can see is that one is liter per capita per day. Okay, so for 100%, this is going to be 100 into 100 is equal to 10,000 liters per day. It's going to come out. Here, liters per day, liters per meter cube per day. That means if you multiply or divide, you are going to get a volume of this one. Am I correct? Correct? So, what we do is, therefore, volume is equal to the discharge divided by the percolation rate. The charge is 10,000 liters per day divided by this 1,300 liters per meter cube per day. So this liter and liter will be cancelled, day and day will be cancelled. So this meter cube will come up 100 by 13. What is my 100 by 13? Where is my calculator? 7.69. This is around 7.7 meter. Okay, 7.7 meter. Fine. Now you know the volume. So the next part is you can assume the depth. So and soffit, don't try to make it. It should not be more than 2 meter because soffit is somewhere that's going to be an open area. If someone falls down, it's very dangerous. So you make it around 2 meters. Therefore, area is equal to 7.7 divided by 2 is equal to 2 3 is 6, 1 7 2 8 is 16.5 meter square. And next one is what you can make it is if you make it if you make the length into breadth, it is of no use to make it length into breadth. Okay. The reason is here it is not going to get to any outlet. Simply all the outlet is going to get here everything is going to get percolated, all the liquids, and once the sludge becomes very thick, that will stop the soffit. Then we will remove it now. So here we are not going to remove it, it's going to lie over there in the soffit. So the length into breadth, it's not necessary. We have to use the soffit to occupy the minimum space. Number one, soffit, try to use minimum space. Because there is no proper incoming and outgoing. Incoming will be there, outgoing is going to be almost percolation over there, right? So minimum area is what we know, it is a circle. Correct? Therefore, this is the area. Therefore, pi by 4, d square is equal to 38.5. Therefore, diameter is equal to 38.5 into 4 divided by pi root over is equal to 38.5, 4 divided by is 7 meter. Finish. Is that clear? So the design of the perfect septic tank and the design of the rural, semi-urban or rural area soffit is designed. Okay. Now let me remind you again, for the septic tank we have 3 zones. The first zone is a mixing zone where the detention period should be around 24 hours or 1 day. And the incoming wastewater, it's going to be 80% of the water demand. And then the lower part of sludge, where it's going to settle down by the biomass, by the cells, you have to make it cleaning for 1 year or 2 years or 3 years, but you have to clean it once it occupies more than 1/3 of the total volume. And the amount of the sludge that is coming out for mixing, it is going to be converted into the sludge in a rate of 30 liters per capita per year. Okay, so these are some of the basic fundamental, and the length to breadth dimension should be 4:1. For a soffit, minimum area, so make it a circular area, and the freeboard should be 0.3 to 0.4 meter. So these are the things of a septic tank. So now the next question is, someone said, sir, I don't have a ladle. Let me rub this part.